Welcome to everyone. We are very happy that you are here in person to the workshop on doctrines and fabrications. The department, the Logic Group of Padua, is very happy to have you here. This workshop is dedicated to the memory of Villa Lovia that colleagues and friends were used to call Ville. And we thought to dedicate the workshop to him because it's about the groundbreaking work done by him in connecting the field of category theory with the field of logic, especially with the notion of doctrine, which has deep connection with the work done by Grothendieck on federation, later by Benabou, and of course it's very linked to Topos theory. So now we remember also that Will gave birth to a new field that is now called categorical logic. I want to express my gratitude to the other members of the scientific committee, namely Samuele Maschio and Thomas Streicher, and to the other member of the organizing committee, namely Cipriano Cioffo, Samuele Maschio, and Peter Sabella. The idea of organizing this workshop came more than 1 year ago, and we started to send invitation last fall, and we tried to have Bill Lovia as an invited speaker here. When last January we heard that he passed away, it was natural to us to dedicate this workshop to him. Lovia's family, in the person of Danilo Lovia, wrote to us to express their gratitude by writing an email which says the following: our best wishes to the organizers and participants in the workshop on doctrines and vibration. We know Bill would have enjoyed participating, and we are honored to have dedicated the workshop to him. We can't help but recall how these ideas have, over the years, been interviewed with our family history. Bill's fourth meeting of Fatma, his wife. His beloved lifelong partner and collaborator was in a Zurich cafe while Bill and John Beck were having the usual intense discussions, and where the paper tablecloth was filled with now familiar objects and errors. They might have been discussing doctrine, a term coined by John Beck around that time. Fatima asked, "What is it good for?" A question Bill loved. And we leave it to you to continue to elaborate this answer. So now I want to thank each of the tutorial and invited speakers who have accepted our invitation here, and to all the contributing speakers who have proposed a talk and to talk here. Last, there is a surprise. Matthias Manning joined the list of invited speakers by giving the last talk on Thursday at 3:20. So thank you for listening, and now I leave the floor to Thomas who will say some words about the purpose of this workshop.
Yeah, so the last year, so from February till February this year, was not only Bill Lovia who left us, but also Jean Benabou. He was the first one, unfortunately, who has a relation with the workshop with respect to vibrations, and also Martha Bunga, the same generation, expert devoting work to Topos theory and using vibrations and things like that. So I'm afraid there were other famous category theories passing away, but at least these three are more closer relationship to what we are discussing now. Well, and in the case of Bill, so if he hadn't done his work in the late 60s or early 70s, we had no reason to gather here. So yeah, you'll soon see those people. And now let's do business. Yeah, Rino, please.
Thank you. I'm really very pleased to have the opportunity to speak here. I realized that there are many people in the audience that are just participating and attending this talk probably out of kindness because they've made it. As the message from Danilo mentioned, some time ago, and not a long time ago, a reasonable question about categorical logic, about, well, the stuff I'm just going to address from an elementary beginning. The right question was to ask was, what is it good for? And it's a fantastic question, and we spent, many of us present here, it's such a pleasure to see you all in presence. It's been a long time we spent away. The digital connections have been very good, but let me say, I've said this already to a few of you, which I met before beginning. It's amazing that we can do it again. It's I feel a bit of pressure because I've not done it for so long to meet with experts and talk about the stuff which is my passion. And the work which has done is being scattered, in fact, at times hidden in places, and it's coming to a reasonable solution, a beginning of an answer to the question, what is it good for? I'm not going to answer that, as Danilo and his family hoped. Maybe there will be answers coming after I spoke during the days. We'll have the chance to discuss them. And let me go and addressing at the beginning the problem with the name, doctrine. Doctrine is a beautiful word. It means essentially what makes us human. But doctrine in the technical sense it has several definitions within the field of category theory and its connection with logic. And I've tried to discuss them, listing two possible ways which are not so separate and which are not so clear, in which one can see doctrines in category theory. As the message says, and I didn't know, John Beck introduced the word doctrine, possibly. One thing I do know, because Bill told me, is that he did not invent the word doctrine, which is, from my point of view, surprising, because Bill, among many other things, was very good at introducing good terminology for mathematical concepts. So, doctrines, in the first, possibly in the first appearances of the word, doctrine meant essentially, and I'm going to be immediately technical, a two-monad on the two categories of categories, of most categories, if you like. To put it mildly, it was possibly an idea of, certainly an idea of Bill O'Leary and possibly of a few others at the same time, of addressing the structure of a logical theory from the point of view of categories. Brutally, in logic, when you look at it from an algebraic point of view, let's say a propositional kind of logic, you think of the poset of consequences, the Lindenbaum-Tarski algebra, if you like, of formulas, and with the order relation induced by the consequence of probability within the theory you work with. As a poset, it is a category, and because there are several operations on formulas, conjunction, disjunctions, implication, whatever, many others by now, that category may have a structure, the algebraic poset of the Lindemann-Tarski, and algebra. And the idea was possibly, I mean, I'm giving you the layman's intuition because I really can offer only that. It's let's raise that structure, which we see at a very elementary level because posets are very simple categories, and see if we can understand theorems about logic from a more structured point of view at the level of categories. And somehow it worked. Somehow. Seeing a categorical structure on a Lindemann-Tarski algebra for a theory suggests to introduce, for instance, Cartesian closed categories for a logic, intuitionistic propositional logic with conjunction and implication. And that's a very nice example, but it's too good an example, at least from my experience. The other variations somehow work, but work often up to a point. After all, it's getting a lot more complicated than just partial order. So it's quite likely that something happens. And the list may go on for very long. One thing that happened in developing this idea of doctrines for categories, if you like, structuring categories to resemble construction from logic, but more specifically a two model on the two categories, led to the introduction of some of the names that you see listed there. I'm not going to go into the details of what they are, and if you don't know, don't worry about it. There is, I want to point out, because maybe I will get to that, maybe, it's just what, 50 minutes? Yeah, so maybe I'll get to that. Regular categories do not appear there, essentially because they are not a doctrine. They do not appear from a doctrine on categories. And then, and this is, and the word doctrine that I've discussed up to now appears in this paper by Bill. Not exactly in this form, essentially because the concept of two category did not exist at that time yet, or possibly did exist but it was not written. So I well, never mind what I was doing at that time. In this other paper, possibly using that ability that I mentioned from Bill's, he introduces the word hyperdoctrine for, well, what I can certainly suggest is a specific example of a doctrine on the two categories, but to refer to an even more complicated structure than just a category, an index category, or a vibration, if you like. And from that point of view, studying logic from the point of view of category theory, well, it has become a field which somehow moved away from the restriction of just being interested in categories and developed another trend. My experience, I got exposed to those when I read the crucial paper on the theory of triposes, and which is a fantastic paper. It's written by, I haven't listed it in the papers, written by Martin Hyland, Peter Johnston, and Andy Pitts, and published, unfortunately, in the Mathematical Proceedings of the Cambridge Philosophical Society, at the time when internet did not exist. Yes, because some of you may not believe that there was a time when internet wasn't there, but yes, that was so. And I even remember one of the three authors giving me a printed version of the paper, and I still have it with the signatures of the three authors on it, saying, but he was giving it to me. I had studied it on the actual volume of the journal, and he was giving it to me, and I couldn't believe. Can I have a copy of it? Even photocopying at that time was not very simple. Yes, of course. I have so many, and I don't know what to do with it. Yes, I know we have destroyed forests with that, but it was a time like that, and well, the copies were not so incredibly many. I think just when. The story here goes on. The extensions to the notion of hyperdoctrine, the variations of the notion of hyperdoctrine are extremely proved to be extremely useful. That is what I'm going to talk about in the remaining few minutes. One direct connection, which is always in the back of my mind when I think about hyperdoctrines. Hyperdoctrines, I said, it's it's an index category. In fact, I'm going to simplify it and think of an index poset, a family of posets indexed by a category, and the indexing is contravariant, so you see always, hopefully, always an off indication up there. But the connection between this and that, as far as I can see, is that at that level you are essentially interested in a single specific hyperdoctrine, index poset, the subobject index poset, the subobject figuration, from a category C into posets. I'm not worried about sizes. If you're worried about sizes, you raise your hand and we'll make sure that things fit at the right levels within any hierarchy of universes you want to mention. So let's start. And this is categories. This is actually two categories. I've said that index posets form a two category. They are a full subcategory of the category of index categories, which is essentially equivalent to the category of Grothendieck vibrations. What are the data for the two categories of index posets? An index poset, as I said, is a functor from the opposite of a category with finite products. I'll try to give you an intuition about why I want to ask about finite products right there, into the category of posets, or the two category of posets, but this is just the one category, so the two level is trivial. I'm looking at it from the point of view of category theory, so I'm not just interested in the structures, I'm also interested in the transformations from one structure to another. And so a homomorphism, a one set in the two category up there, is a pair of transformations from the category and from the functor. So it is a functor which preserves finite products from the category B to the category C, which is the base for the other index poset, together with a natural transformation here from if you've never seen this, careful now, from this functor into the composition of the opposite functor F bar and the index positive Q. This composition is a functor from the same category B as the functor P, so I can talk about a natural transformation there. Okay? I'm just saying it fits the picture. Don't worry about why or what it is good for. It's a two category, so it's not over. We've taken the structures, the homomorphisms between structures, and now we want homomorphisms between homomorphisms. And well, you just follow your nose in category theory. The structure is there, use it. So now we have to take two homomorphisms, F and G. F bar is the functorial part from the base category. F hat and G hat are the second part, the natural transformations. And it is a natural transformation there, which gives rise by opposition to a natural transformation in the other direction, which allows you to consider two triangles there. One is the triangle which you fill in with the natural transformation F hat, the other is the triangle you fill in with the natural transformation G hat, and one asks that the two are connected by a less than or equal. It's a notion which, in a sense, gets pictured much better when you remember that index posets are index categories and they are fibrations. As fibrations, well, if you have never seen the construction that turns an index poset into a fibration, sit tight here and attend the next few talks because you see it repeatedly. I'm not going to go through that. It's just that it allows you to change all the data. It's a beautiful construction. It's probably the right way to do it. I'm not going to do it. I'm sorry. You construct another category out of the data P with a very canonical functor. You can't fail to see it from that category into the category B. There is no op anywhere appearing, and all the data as I presented here turn into the canonical picture when you look at arrows in a category and commutative diagrams of arrows. So the data of the one cells turn into commutative squares from this functor into that functor, and the notion of two cells, homomorphism of homomorphism, turn into a pair of natural transformation, exactly that. One has to require a few conditions on natural conditions on the fibrations. But I'm not going to go into that, otherwise I will spend the time of the tutorial just on that. And just to go back to the idea of doctrines in one sense and doctrines in the other sense, this is a possible connection. I'm not sure this may explain the reason why Bill used essentially the same word for two distinct concepts, but they were not very distinct. And if you cannot read this statement, don't worry. It says essentially that from the point of view of category theory, doctrines are form an algebraic, the models for an algebraic theory on categories. And here is the first elementary definition on the structural doctrine. And it appears as a notion in several papers. Unfortunately, it appears in most of them with different names. And since she forced me to introduce a fixed notation for the concept, it has remained fairly stable. And it's very simple. It's a primary concept. It's a concept for primary schools. Well, I gave you time to read it. I'll go quickly through it. It's an index poset, so the category B has finite products, and all the posets PB for B and object, little b and object in the category B is a poset, and I ask that poset be an int semilattice, so it has finite means. Maybe I should stop here to make a remark. The idea that logical concepts should be introduced as categorical concepts, and especially as adjoints, comes from me. From my point of view, from my experience, it has been an illuminating intuition. I see any construction when I teach an elementary course in mathematical logic. I do not mention adjoints, and I feel very guilty, but my intuition behind it is always that, and I speak to students with that intuition in mind, and they sort of understand logic. In fact, often enjoy it rather than think it is trivial and useless. And moreover, well, it's category theory, what do we expect? These families of a right adjoint, in this case they are right adjoints to standard constructions, have to be natural when you look at the indexing that they are provided with. Natural. Naturality, when expressed directly, is a collection of a pair of collections of identities. One has to do with that operation. There is a C here, which is a B there. I thought it was a typo. It's not a typo because the PF, being contravariant, moves things around, goes in the opposite direction, and so you first intersect two elements and meet two elements, and then you change them, and that's the same as changing them first and then taking their meet in the new poset. So it is just that. It's putting all things together. It looks messy, but category theory allows you to do it very cleanly. Examples. And I thought that the first example I should mention is exactly the one coming from logic. Take a theory in the simple fragment of with just conjunctions of formulae in first order logic. The base category, B, is the category of complex. One thing that usually is not taken care of in a elementary course in mathematical logic is to declare, contextualize formulas, to declaring variables on which those formulas must be built. It's something that I've learned from computer scientists, because they knew the value of declaring variables before you start writing things. Mathematicians always assumed that variables were obvious from the context, which is exactly what context makes. It's you just write it. So you write a list of variables. They have to be distinct, because when you take an arbitrary element, it's arbitrary, so it cannot be one of those which you have already introduced before. And arrows, because it has to be a category. Arrows are a list of terms which can be written in place of the variables in the target, and these terms are written using only these variables. Not necessarily all of them, but no other. Certainly not. Then the where is it? Then going opposite from this category, it is a category. Oh yes, it is a category. Sorry, I forgot the main construction, which is that of composition of two lists. But it is just what I suggested. These T's can be written in place of the X's. Suppose there is another list of terms here, which are written using these variables. In these terms, you write these other terms replacing these variables. It's just substitution, as one says. The fibers, the various PVs, well, they depend on a list of distinct variables, and it's the Lindenbaum-Tarski algebra of the formulas, in this case, conjunction of formulas in the language, with the order induced by the consequence, the probability consequence in the theory. If you think it's not an order, well, it is the Lindenbaum-Tarski algebra. So in fact, it's not just formulas, it's equivalence classes of formulas quotiented by equiprobability integral. And one thing I've written down carefully is to check that that condition is satisfied. I've not checked that it is a factor. So what I want to do is to take the action substitution of an arrow, a list of terms in the base category, that of context, on a conjunction. And as I said, is the formula where the variables are substituted by the term. So, well, substitution, I don't even know if this is often written in textbooks in mathematical logic, it's just substitution. There is no way I can substitute x's in this symbol because it is a symbol, and in fact, one knows that substitution distributes over conjunction or whatever. It does just that. It distributes canonically on the two conjuncts, but what I've written here is exactly the substitution, the action of the functor on the first formula, the substitution here, and the substitution of the terms here. So it is the conjunction in the other person. So that is satisfied. It is easier to prove that, check that, and it is a primary doctrine. In fact, I should say that these examples coming from logic are the intuition that I usually have about doctrines. Because of the way it gets written, substitution, very often the action of the functor PF, a monotone function from the poset P of C into P of B, is written just like that. It's not application, but it looks like applications. If I don't know, I always think in terms of polynomials because that's where I learned how to substitute. If this were a polynomial and I had to substitute values into the variables, I would have written exactly like that. But then they are not polynomials, they are formulas, but well, what's the difference? Other examples, and now technicality becomes really quick. The main example, the power set, the contravariant power set function from the category of sets opposite into posets, to each set associate the power set on that set with inclusion, to each function write consider the inverse image along the function which goes backwards, which is something I remember caused me headaches in my first year at the university because I really couldn't understand it. And that's why probably I'm not doing so well in category theory. The subobject factor is just another example, as I mentioned, but it is primary when necessarily the category C has finite products. I mean, that is a condition on the primary doctrine, so that has to be paid in. But then you see immediately that the fact that they're using all subobjects, it's not really necessary. One needs just a collection of monos, a specific collection of monos with enough closure conditions. Because of this, because of the contravariant power set, often the notation which you see employed is something like this, and not PEF, because PEF is clumsy as a notation. And another example which takes me into something more interesting. Consider a category with just weak pullbacks, and instead of taking the sub-object, the poset of sub-objects, take what you would hope were a poset, but it isn't, and it's where you fail to require that this arrow is monic, and that arrow is monic. When this arrow is not monic, you have no way to prove that a commutative triangle is available just once if there exists a leg, which is necessarily unique, and so you fail to have a poset, which is very good because you get what is known as the comma category over the object A. But I want a poset, so given a category, reflected to a poset. Say that an arrow into A is less than or equal to than another arrow into A when there exists a commutative triangle. If there are 2, 3, whatever number of triangles which make this commute, it doesn't matter. It's already less than or equal. It's not a poset, as I said. You have to quotient equivalence classes, just like the formulas, equivalence classes to force that reflexive and transitive relation to an antisymmetric one. So that is the poset reflection. That is the category of variations. Was suggested by Bill. I must admit, I'm not sure I can point directly my finger to one of his papers, but you can read about that suggestion in papers by Marco Grandis and Walter Tolan about variations. The name variations come from them. Because I requested weak pullbacks, when I consider a weak pullback diagram of a representative for an element in there along any arrow, I get, thanks to the quotienting that I've done, I get a monotone function from this poset to that poset, and that's all I need to introduce another notion of primary doctrine. Again, I have to make sure that I have the basic condition on the category. So weak pullbacks are not enough, and I want strong, real, categorical products, finite products, on the category A. So it's a bit of a slanted condition because there are certain strong limits, finite products, but then weak finite limits in general. Again, because of these examples, a possibly better notation than the previous one is that of not just writing -1 up there, but just a little star. And I mean, you read papers and you have to navigate through the various notations you find in the papers because they change depending on the attitude of the authors and of the subject at hand in particular. Another example, take an if semi-lattice and consider, well, an extension of the power set factor where h is just 2, which takes a set to the power of the if semi-lattice with that set. So it's common to think of this as h-valued properties of the set S, which is a very nice intuition, I think. Then the action is written a lot more easy than what I've done so far. It's just precomposition. Because of that, guess what? This is again the notation, but since it's just precomposition, it gets simplified to that. No parentheses. I mean, is it better? Is it worse? I don't know. It depends on the context, really. something that I want to mention that is again related to the connection between the two different notions of doctrines that appear in the literature. When you look at index poses on a category B, well, let's say B as finite products, but it really doesn't matter in order to make this connection. But what you're doing, fixing the base B, is exactly the same thing as taking posets in the topos of presheaves on B. It's exactly that. And the forgetful functor that takes, well, whatever category of primary doctrines one hooks up into index posets, presents exactly the semi-lattices in these Grothendieck topos. So, from the point of view of logic that Mickey and Thomas were mentioning at the beginning, doing all this, in a sense, is just performing the theory of the algebraic theory, possible, of semi-lattices within a universe of topos produced by a Grothendieck topos. Because of that, all right, good that I wrote, the action that you see can be written with the notation used for presheaves in the case of toposes, with the restriction sign and the arrow F acting as if it was a subset. Oh, the other two notions of primary doctrines that I would like to mention, it's existential. Again, it comes from one of the papers of Bill, and it is existential when, well, some other structure is on it. Rather than going through the details, they are very similar. It's this time it's a left adjoint determined by a structure of formation which gives a natural collection of operations which satisfy a particular condition, which expressed directly without mentioning naturality gives this time an identity of this kind. I've written it explicitly because I wanted to make sure that one could understand that the projections I were referring to were clear, not having to refer to context, and I just wanted to make sure that we understand what I'm writing. So I'm taking the two projections. I've asked that certain things exist along first projections, and if I notice that in this diagram the unique arrow that exists here is that, because that's the way one writes it, but it's actually has to be, since it's unique, the identity from there to there, one sees that, what am I doing? Yes, that notation can be clumsily rewritten, writing the action of the identity on this side. But I've done it because using the notation with the round parentheses, it made me think that P1 is my notation for a variable, like P2 is my notation for a variable. And in a sense, here I'm considering alpha, which is in dB, as alpha of a single variable, and beta, which is in here, as a formula in two variables. And something happens in that identity. And then, if instead of mentioning, I mean, why have I used an upside down E as a notation? Well, instead of marking the projection which I've used in order to introduce it, I subtract the projection I'm not using, and avoiding the fact of using a letter because I really don't know what to do with that letter, and I write it like this. Here, if I read that thinking logically, I'm saying I'm not sure I can read it, there exists P2 such that alpha P1 and beta P1 P2 is equal to, equivalent to, alpha ha of nothing. And there exists P2 such that beta of P1 P2, which is a standard way of using the existential quantifier, because this does not depend on P2. But P1 is not there. But P1 is there, as long as I take the right P1, because this object is the product of that object, the single product with one factor, and the single projection, P1, it's the identity. In fact, I construct it like that. So I can write there the identity, and I just mark it P1. I know this P1 is not the same as that P1, but are you always so careful when you write three variables in formulas and think, oh, this formula is within that context and that formula is within that other context? No, it's obvious from the context. I think it's good mathematical hygiene to have this in mind. Yes, this is the idea behind it. And I can do the same trick for the other identity, and I do it very quickly. By the fact that you laughed, you appreciated the change on that, I've done it already, and then I'm going to change those two using the right P's, and that's it. And this, well, look at MDF, which moves from out to in, and this is just substitution. Well, yes, you have to be careful that the variables which appear in F are not caught within the range of the quantum. No, forget it. The context takes care of that, and that's it. It's a lot cleaner without having to write all the provisos which we write when we make substitution of quantified formulas. Yes, the intuition about that is the existential quantifier. The examples are, well, I suggested it. Take now a theory where you can write existential quantification as well as conjunctions, and it gives you just performing the same construction we've done before for the example of primary doctrine, and it gives you an instance of an elementary doctrine. The power set is powerful. It's always there. The power set factor is existential. Now, when you take some objects or particular sub-objects given by some monos, that in this case must come from a stable factorization system, which is disturbing, but it's also good to know. I'm not going to get into that. In particular, the sub-object index coset works as an existential doctrine when C is regular, which, remember, is a notion which is not given as a doctrine as a two-monad. The case of a category with finite products and weak equalizers or pullbacks and weak pullbacks is an example of existential doctrine where the existential quantification is just performed by composition. It works almost by definition, and well, unfortunately, you need to require a lot on the insimilatis that produced a primary doctrine in order to get also an existential doctrine, because the left adjoint that you can compute require that the lattice be complete and also satisfies the form of distributivity with respect to the conjunction. And these are the examples. And the way to see existential doctrines as particular posets in the topos of presheaves on the category B, once you fix the base, And it is to see that the functors that were actually involved in the definition of the structure, the left adjoins to the reindexing along a first projection, are just a notation for a specific exponential in the topos of Precious. This is not an exponential in sets. It doesn't work. But the miracle that happens in the Grothendieck topos is that it turns that very clumsy construction into a very clean construction, and the adjointness condition just says that the operation is performing a soup over families of elements, thinking in terms of the internal logic of the Grothendieck topos, families of elements of the poset indexed by these specific objects. And it all requires the Yoneda embedding, which I'm not going to go into the presentation of because, well, I'm sure you know about it, or at least believe it. And the final notion of doctrine that I wanted to mention, being elementary. The notion of existential elementary doctrine appears in Bean's paper on equality in hyperdoctrines and the comprehension scheme as adjoint functors. And the notion of elementary is again an existence, the requirement of existence of structure as left adjoint to other very specific substitutions, reindexing functors. If consider the case where B is the terminal object, so here essentially I'm writing an arrow from C into C cross C, and the arrow I'm writing is just the diagonal with the two components which are the identity, is P2 repeated to C. It's not P1 repeated, but it's P2 repeated, and in that case it will look like the identity. So it's essentially a left adjoint to reindexing along identities, parameterized identities in fact. The condition on the left adjoint is similar to that before. Oh, by the way, I didn't say that FR is an acronym for radius reciprocity, which is the way distributivity, if you like, is named in this situation. And again, this family is natural in the index. Examples, well, yes. The power set, contravariant functor, is an example of that. It's easy because you learned it when you performed elementary set theory, that every inverse image function has a left adjoint, and in particular the inverse image function that is defined like that, whatever complicated it is, has a left adjoint, and they do satisfy these, they have to satisfy those. It works also in the case of a stable factorization system of C, because in fact you do prove that you have all adjoints, left adjoints through reindexing. But then there is a characterization for primary doctrine, for elementary doctrines, which find that the primary doctrine is elementary if and only if these three conditions are satisfied. And I guess I want to write them using the formula-like notation, so I'm turning the reindexing action on the right and write them as if they were variables, and it is written that beta of P1 and delta of P1, P2 implies beta of P2. I'll read it again. Beta of P1 and P1 equal P2 implies beta of P2. I can substitute equals by equals. In fact, it is true that P1 is equal P1, wow. And the third one says that if P1 is equal P3 and P2 is equal P4, there are too many. P1, P2, P3, P4. Okay, they are those. And in fact, this is a product of products which have first projection and second projection, because I have to think in terms of first projection and second projections, because that's the way the definition is given. And the first projection is obtained into this product by pairing these two. There they are. The second projection is obtained into this one by pairing these two. There it is. And so, if I pair first projection and second projection, we've learned that we obtain the identity from this product into itself, which is the thing I've written here because it was missing. And it was missing because it was the identity. And so, it's obvious, the identity, I never write it. Well, no, in logic we always write it. As here it says, if P1 is equal to P3 and P2 is equal to P4, then the pair P1, P2 is equal to the pair P3, P4. Got it? It was written there. The left adjoint in this situation, because I mean it's just an algebraic condition, is written like this. I've rewritten in formula-like notation, and the left adjoint is written, so it's acting on a beta now that has two variables. I mean, let's simplify things. So it's beta of P1, P2, conjunction with meet P2 is equal to P3. And it becomes with a useless variable, P3, because after all P3 is equal to P2, but it becomes a formula in three variables, which is some of the games that the logicians like to play all the time. So it's just like that. It is a quality. And in fact, this idea of equality, and I'm going to wrap it up, it gives us the possibility of checking other examples. So the category of context, this time, I need a language with equality, and it works. The sub-object vibration, I see with finite limits, works. There are the diagrams. I'm going to leave the slides available. If you need to check the pullbacks, that has to be checked in order to check these three. They are written up there. And finally, in the case of the insemi-lattice H, well, one needs a possibility of right Kronecker delta. And so there need to be a least element to write the other condition for the equality. For two categories now to finish. So the category of primary doctrines, it's what you expect. You preserve the structure that has been added on in the corsets. So that's the preservation condition. I've written it just to make sure that I know what diagram I had to chase, and two cells are exactly the two cells of index corsets. The elementary doctrines, well, I've added certain operations, and I need to require that the homomorphism preserve those operations. And then the existential doctrines, I've added other operations, and those have to be preserved. And there is, as I mentioned, the joint condition of being existential and elementary at the same time. The doctrines for doctrines. The doctrines, in the first sense, I mentioned at the beginning of the tutorial, and the doctrines have been presented throughout. They are all, well, the correct terms is pseudo-algebras for an appropriate two-monad or two-co-monad on the category of primary doctrines. And in fact, in here, Davide has proved that also the existential doctrines are pseudo-algebras. The existential, I'm sorry, the existential elementary doctrines, there is something missing there. Sorry, David. and I want to just let you look at the construction of the end of factor for the doctrine, no, for the comonad, for the two comonad, no, for the lax, for the co-lax idempotent two comonad on primary doctrines, which makes the trick. And given a primary doctrine, you construct a category which is a category of pairs. The pairs are an object of the original category and something in two variables. Well, can I write it in two variables rather than writing it like that? Rewriting it immediately in two variables, such that it is true that row of P1, P1, if row of P1, P2, then row of P2, P1, symmetry. And if row of P1, P2 and row of P2, P3, then row of P1, P3, transitivity, they are usually called these objects the equivalence relations, amazing. And the arrows in the category, I'm still defining the base category, are original arrows which preserve the relation. And now, in order to define the posets indexed by the objects P row, I define the posets of descent data, which are just those properties on B which are stable under the relation. Yes, I have to finish. I wanted to write this down on a slide because it's just the beginning of where it all went. Mimi got me involved in doing this, and I'm very grateful that she did that. After that, contributions by many people, Fabio Pasquali, Jacopo Emenegger, Davide Trotta, Greta Coraglia, Francesca Buffanti. I'm realizing I'm mentioning just Italian names. Cipriano Giulio Ciofo, Samuele Maschio, oh my god. Valeria De Paiva, it sounds Italian. Thomas Stryker cannot be Italian. Jan van Lusten, Benno Vandenberg, and I'm sure I'm reading many others. Jonas Fry, who am I forgetting? It's been a fantastic collaboration on what I think is a really beautiful subject, which has still to bring fantastic fruits. Thank you very much.
Thank you, Dino. I mean, you've exhausted your time quite well, and coffee is waiting, but maybe a quick question.
You said something at the beginning. Oh, thanks. Thanks for the talk. It was really good. You said something at the beginning which I found very surprising. Could you elaborate more on why regular categories aren't examples of doctrines?
And
You said that they aren't.
yes, because I don't know a way to construct them,
Okay.
and I know they are not one monadic of a cat, so that's already something.
Mm-hmm.
And I also believe that some of the results which I've skimmed rapidly through would actually prove that they may be in some form a doctrine of vibrations or index posets by using one of these constructions. Essentially it's because of the failure of one monadicity of a cat. But that's all I know. And if this result, in fact, already appeared in modified form somewhere, then it's my ignorance. And if you know more, actually, I will.
No, it's because when you say that they're not doctrinal, it's in the sense that they don't appear as from an injunction rather than that you can describe them using some object?
It's more than that.
Okay.
It's they appear from an adjunction, which is an adjunction given by a monad or a co-monad on that category, and so it's monadicity what I'm really looking for. They have to be all algebras for a certain doctrine,
Right.
not just specific algebras. Thank you for the question. I'm sorry, I yes, certainly was too quick on that. Yes.
Jonas?
So you also said that the exact categories do come from a two-monad cut. And
Well, I didn't say that so explicitly. Yes, but yes.
yeah, I wasn't aware of that. That's nice. Is this? Do you have a reference for that, or do you do it as? Can you just do it in?
Where is that? You can check with me.
Okay. Okay. Yeah, then I'll.
So you have something to discuss at the coffee?
But in fact, well, I mean, yeah, please discuss that. It would be perfect if you do discuss about it.
It's
Because
not
you
a
want so
question.
much about it, yes.
Yeah.
It's not a question, but could you just put back that diagram that you flashed through, which had
Many.
that kind of had a posset on the left, so that I can think about it over the coffee.
Okay.
This one,
No, the one that had just a hassle. No, yeah, that one.
this one.
That one.
Yeah.
I just want to think about.
Mind you, I'm not saying that this is some kind of intersection. It has to be done very. It's just a collection of inclusion of two categories. Sometimes are two full. None of those is one full. So it's just.
Okay,
That's
so
great. Thank you.
there's something to think. And yeah, thank you, Bruno.
Good, good, good. Let them go.